Look up at the night sky. What do you see? A black, empty void, punctuated by tiny, twinkling points of light. It's a view that has inspired poets, philosophers, and scientists for millennia. It feels serene, eternal, and, if we're honest, a little bit empty. We call space a vacuum, after all. But I'm here to tell you that this is a cosmic illusion. The greatest magic trick the universe ever pulled was convincing us that there's nothing there. In this series, Stars from Birth to Death, we are going to pull back that curtain. We are going to witness the entire, dramatic life cycle of the stars, from their silent, invisible beginnings in what we mistakenly call nothingness, to their spectacular, universe-shaping deaths. It's a story of chaos, violence, and breathtaking beauty. And it all starts not with a star, but with the void between them. I remember a night a few years ago, high in the mountains, far from the glow of any city. The sky was so clear, so utterly black, that the Milky Way wasn't a faint smudge. It was a raging river of light, a thick, textured cloud of countless stars. It felt close enough to touch. In that moment, I didn't just see the stars. I felt the space between them. It wasn't an empty void. It felt like a presence, a canvas. And in that moment, a question seized me, a question that had never felt so urgent. If this is the canvas, then what are the brushes? What are the paints? Where does the artist begin? The answer, I would later learn, is hidden in the apparent emptiness. The cradle of stars is not a place of nothing. It is a place of potential. And tonight, we are going to find it. For centuries, we thought of interstellar space as a perfect vacuum. The dictionary definition of a vacuum is a space entirely devoid of matter. By our comfortable earthly standards, space might as well be. But this is not strictly true. It is not empty. It is filled with the ghost of creation, the whisper of what was, and the promise of what will be. Between the stars of our galaxy is what is known as the interstellar medium. Think of it not as empty space, but as an incredibly thin, incredibly diffuse atmosphere for the entire galaxy. It is comprised mainly of hydrogen gas, the simplest and most abundant element in the universe, followed by a small amount of helium, and trace amounts of heavier elements, the very stuff that makes up you, me, and our entire planet. We call these traces metals, and they are the ashes of long-dead stars. A crucial point we'll return to again and again. Now, when I say incredibly thin, I mean almost incomprehensibly so. Let's get our heads around the numbers. In the densest parts of this interstellar medium, there might be about 1 million molecules per cubic centimeter. That may sound like a lot, but let's hold it up for comparison. In the same single cubic centimeter of air you're breathing right now, at sea level, there are about 10 quintillion molecules. That's a 10 with 19 zeros after it. The difference is staggering. Even in the best laboratory vacuum we can create on Earth, there are still around 10 billion molecules in that same cubic centimeter. But out in the more sparse, desolate reaches of space, the interstellar medium's density can plummet to less than one single lonely molecule per cubic centimeter. Imagine a single grain of sand in a vast, empty cathedral. That's the scale of isolation we're talking about. But what does this mean in figures we can actually wrap our heads around? Well, here's an analogy I've always loved. If you're sitting on a chair, look directly down at the ground. Imagine a cylinder, the exact diameter of your pupil. drawn from your eye all the way to the floor. The number of air molecules in that cylinder is immense. Now, imagine you are sitting at the very edge of our solar system, in the cold, dark realm of the Kuiper Belt. Picture a cylinder of the same diameter, but this time drawn from your eye all the way to the center of the Milky Way galaxy, a journey of over 27,000 light-years. The number of molecules from the interstellar medium in that unimaginably long cylinder is less than the number of air molecules in the tiny cylinder from your eye to the floor. Let that sink in. The space between stars is emptier than any vacuum we can conceive of. And yet, despite its ghost-like tenuity, this interstellar medium is thought to make up roughly 15% of the visible mass of the entire Milky Way galaxy. That is a phenomenal amount of mass when you consider it's being compared to the hundreds of billions of stars that make up our galaxy. This faint, diffuse mist is one of the universe's most important players. It is the raw material for everything. This medium isn't just a passive cloud of gas. Much of it is ionized, meaning the atoms have been stripped of their electrons, creating a soup of charged particles. We can actually see this. There's a special scientific instrument called the Wisconsin H-alpha Mapper WAM, which is designed to see the faint glow of ionized hydrogen gas throughout our galaxy from our perspective on Earth. And when you see its data mapped onto the night sky, it's breathtaking. It reveals a sky alive with faint, structured veils of glowing gas. It gives you the immediate and powerful perspective that there is a lot more stuff out there than your eyes alone would ever lead you to believe. The galaxy is not just stars and blackness. It's a complex, dynamic ecosystem of gas and dust. This interstellar medium, particularly the dust, has a very real and direct effect on what we see from our little planet. Over the vast distances between stars, this dust acts like a cosmic fog. It either completely blocks our view of stars thousands of light-years away in the visible spectrum of light, or it scatters the starlight, giving distant stars a reddish appearance, much like our own sun looks red at sunset due to dust in our atmosphere. This is a crucial point. If there wasn't an interstellar medium between the stars, the night sky would be utterly, blindingly brilliant. You would be able to see the entire disk of the Milky Way in all its glory, a blazing arch of uncountable stars from horizon to horizon. The fact that we see a relatively dark sky with distinct stars is, in itself, proof that something is in the way. Filtering the light. The interstellar medium is that filter. As I mentioned earlier, this medium isn't evenly distributed. It clumps and gathers. The densest regions of the interstellar medium are what we call nebulae, from the Latin for cloud. Some of these regions appear as dark holes in the bright band of the Milky Way. In actuality, they are not holes at all. They are massive, cold, interstellar clouds of gas and dust, so thick they block the light from the stars behind them. And when I say massive, I mean on a scale that defies human comprehension. I'm talking many light years, across dozens. Some of these clouds can be many millions of times the mass of our sun. They are the celestial mountains of gas. You have almost certainly seen one of these nebulae before. Even if you didn't know what you were looking at, you've seen the pillars of creation. This famous Hubble image is one of the most iconic photographs ever taken. What you're looking at is a stunning example of these colossal gas and dust clouds. It's not a painting, it's a real place. To give you a sense of the sheer scale, the leftmost pillar in that image is about 4 light-years long from top to bottom. Just to give you some perspective, one single pixel in that higher resolution image might just about cover the entire diameter of Neptune's orbit. If our solar system was placed right next to the pillar, our entire local cosmic neighborhood would be a speck on this structure. Incredibly, however, this breathtaking image is in fact just a tiny segment of a much larger nebula known as the Eagle Nebula. This nebula, and countless others like it scattered throughout the galaxy, are the stellar nurseries. These are the places where stars are born. Let's look closer at an image like the pillars of creation. In the background, you can see those beautiful, ethereal colors of greens, blues, and reds. These bright, glowing regions are known as H2 regions, pronounced H2. They are vast clouds of ionized hydrogen, lit up like a cosmic neon sign. The process is actually very similar to what happens in a neon light. The hydrogen gas is being bombarded by intense ultraviolet radiation from nearby, already formed, hot, young stars. This UV radiation energizes the gas, stripping electrons from the hydrogen atoms. When those electrons eventually recombine with the atoms, they release that energy in the form of light. Different atoms produce different colors. In these Hubble images, the specific color palette is often chosen to represent different elements: green for hydrogen, red for ionized sulfur, and blue for doubly ionized oxygen. These H2 regions are extremely hot, heated by their stellar powerhouses to temperatures over 8,000 degrees Celsius. They are also reasonably dense for the interstellar medium, ranging from 100 up to 10,000 molecules per cubic centimeter. Now, contrast that with the pillars themselves. These dark, towering structures are known as molecular clouds. These are the densest, coldest parts of the interstellar medium. Their density can range from around 100 to an astonishing 1 million molecules per cubic centimeter in their deepest cores. And they are cold, unimaginably cold. Although I've talked about all this matter-of-factly, it's vital to remember that this is still a theory, a very well-supported one, but a theory nonetheless. Actually, directly observing the formation of a single star is incredibly difficult due to the vast timescales involved and the fact that these protostars are deeply embedded within those same thick, obscuring dust clouds that give them birth. We are, in a sense, trying to understand the birth of an elephant by only seeing the outside of the womb. This is one of the huge advantages of telescopes, like the James Webb Space Telescope. Its revolutionary ability to see in the infrared part of the spectrum gives it a massive advantage over Hubble. Infrared light has longer wavelengths and can pierce through the thickest of dust clouds, allowing us to peer directly into the stellar nurseries and hopefully, for the first time, watch protostars in the act of formation, to see the very first cries of light in the cosmic cradle. So, we have our trigger. We have our collapsing cloud. We have our growing protostar, a raging, spinning, chaotic infant, glowing with the heat of its own violent birth. It is surrounded by a disk of material that may one day become planets. It is on the cusp of stellar adulthood. But it is not a true star yet. It's still just a massive, hot ball of gas, shining from gravitational energy, not nuclear fire. The transition to true stardom requires one final, definitive, and spectacular event, a moment of ignition. So, the question that hangs in the air as we look at this cosmic newborn is this: what is the final, critical transformation that must occur in its searing, pressurized core to cross the threshold and truly become a star? I want you to picture a nursery, not a quiet, pastel-colored room, but a place of immense noise and violence, a place where the very forces of nature are locked in a titanic struggle. This is the reality of a stellar nursery. We often look at images from Hubble and Webb and see these beautiful, serene clouds of color, and our minds interpret them as peaceful. It's a natural illusion. The truth is, the birth of a star is one of the most violent, chaotic, and destructive processes in the cosmos. It is a battle for existence, a gravitational gladiator arena where the victors win the right to shine for billions of years, and the losers are condemned to a slow, cold fade into obscurity. In this chapter, we are going to step into that arena. We will feel the heat of the impact, hear the silent roar of the accretion, and understand the precise, unforgiving physics that separates the stars from the failed dreams. And we will come face to face with one of the galaxy's most numerous, yet most hidden populations, the brown dwarfs, the ghosts of stars that never were. Let's pick up where we left off. The trigger has done its job. A region of a molecular cloud, perhaps several light-years across, has lost its supporting internal pressure. Gravity is now the undisputed master. Within this collapsing cloud fragment, density fluctuations have created dozens, hundreds, even thousands of individual knots. Each knot is a race against time, a gravitational pit pulling in everything it can as a knot collapses. It doesn't do so in a neat, spherical fashion. The cloud has some inherent, tiny amount of rotation, a leftover momentum from the galaxy's own spin. As the cloud contracts, this rotation speeds up, obeying the conservation of angular momentum, the same principle that sees an ice skater spin faster as they pull their arms in. This rotation forces the infalling material to flatten. What was a roughly spherical clump begins to morph into a system, a central, growing condensation, the protostar, and a spinning, flattened disk of gas and dust encircling it, known as an accretion disk. This disk is the lifeblood of the infant protostar. It's a chaotic, high-energy environment. Particles within the disk collide, stick together, and slowly migrate inward, spiraling towards the central gravitational well. The temperature in the inner regions of this disk can soar to thousands of degrees. The material doesn't just fall onto the protostar peacefully. It plummets at tremendous velocities, often being channeled by the protostar's nascent magnetic fields onto its poles in powerful, focused streams called accretion columns. When this supersonic flow slams into the surface of the protostar, it releases an immense amount of energy, creating brilliant hotspots and raising the protostar's temperature to a blistering glow. We have actually seen this. While the thick cocoon of dust often hides the protostar itself, instruments that can see in infrared and millimeter wavelengths have captured stunning images. One of the most famous, from the Atacama Large Millimeter Submillimeter Array, ALMA, shows a protostar within a dark cloud named BHB 200711. In the image, you can clearly see the dark, dusty disk edge on like a hamburger, and emanating from its poles are two spectacular, opposing jets of material shooting out 4 light-years into space. These jets are a direct byproduct of the violent accretion process, a way for the system to shed excess angular momentum. They are the protostar's first scream into the cosmos, a declaration of its tumultuous existence. This phase is known as the Class 0 and Class 1 protostar stages. At this point, the object's luminosity is dominated almost entirely by accretion. It is not a star. It is a gravitational engine. The core is getting hotter and denser, but the primary source of the light we see is the sheer kinetic energy of infalling material crashing onto its surface. It's a spectacular but unsustainable way to live. The protostar is essentially burning its fuel tank as a source of heat, not by igniting the fuel itself. All the while, deep within the core, a silent, relentless pressure is building. The weight of the overlying layers, the entire mass of the accretion disk, and the outer envelopes of gases crushing down on the center. Imagine the deepest part of the ocean, but 1,000, 1,000,000 times more intense. Atoms are packed together tighter and tighter. The temperature soars. It passes 10,000 degrees, then 100,000. The gas, once neutral, becomes a searing plasma soup of bare atomic nuclei and free electrons. This is a race, a desperate climb towards a specific physical condition. The protostar is trying to reach a core temperature and density so extreme that it can initiate the universe's ultimate power source, nuclear fusion. This is the finish line. This is what separates a protostar from a star. But there is a catch, a critical, unforgiving threshold. The universe has set a minimum entry fee for stellar citizenship. A protostar must achieve a mass of at least 0.08 solar masses, about 80 times the mass of Jupiter, or over 26,000 times the mass of Earth. This is not an arbitrary number. It is calculated from the fundamental laws of physics. It is the minimum mass required to create a core gravitational pressure so immense that it can heat the plasma to approximately 10 million degrees Kelvin. At 10 million degrees, something magical and terrifying happens. The thermal motion of the hydrogen nuclei, which are single protons, so violent that they can overcome their immense natural electrostatic repulsion for each other, like trying to push the positive ends of two magnets together. They get close enough for the strong nuclear force, which operates only at infinitesimally small distances, to take over and fuse them together. This process is known as proton-proton chain fusion. In a series of steps, 4 hydrogen nuclei, protons, are fused into one helium-4 nucleus. But here's the crucial part. The mass of a single helium-4 nucleus is slightly less than the mass of the 4 protons that created it. This missing mass, according to Einstein's famous equation, E equals mc, has been converted into a staggering amount of pure energy. This energy, in the form of gamma-ray photons, is what will power the star for millions, billions, or even trillions of years. The ignition of fusion is the moment of true birth. It marks the transition from a protostar to a main sequence star. the star achieves a state of beautiful, stable equilibrium. The outward pressure from the heat generated by fusion in the core now perfectly balances the inward, crushing force of gravity. The star stops contracting. It finds its size, its temperature, its destiny. It has joined the main sequence, the adult phase of stellar life, which we will explore in the next chapter. But what if the protostar loses the race? What if the food runs out before it can cross the finish line? This is the cosmic tragedy I mentioned. The molecular cloud is a finite resource. It is being consumed not by one, but by hundreds of protostars simultaneously. Furthermore, the most massive of these protostars will ignite fusion first and begin to blast the surrounding cloud with fierce ultraviolet radiation and powerful stellar winds, like a cosmic bull in a china shop, violently dispersing the very gas that feeds its smaller siblings. If a protostar is cut off from its accretion disk before it can gather that critical 0.08 solar masses, its fate is sealed. It will never achieve the core conditions necessary for sustained hydrogen fusion. Its climb towards ignition is halted. It becomes a brown dwarf. A brown dwarf is a failed star. It is a celestial object that lives in the murky gap between the most massive planets and the least massive stars. The name itself evokes something dim, unfinished, and obscure, and that is precisely what they are. We're talking about minus 260 degrees Celsius, just a handful of degrees above absolute zero, the temperature where all molecular motion stops. Because of this incredible density and cold, they don't allow light to travel through them very easily. In fact, they would be almost completely invisible to us if it wasn't for the fact that they are often silhouetted against these brighter glowing H2 regions behind them. They are the dark, brooding giants of the interstellar medium. And here lies the incredible, almost paradoxical secret. It is within these cold, dark, and seemingly lifeless clouds, these cosmic freezers, that the furnace of a star is born. The very material that blocks the light is the same material that will one day ignite it. The dust and gas you see in the pillars of creation is the same dust and gas that will collapse to form new solar systems, new planets, and perhaps, one day, new life. But there's a problem, a big one. A show-stopper. These massive molecular clouds are, generally speaking, stable. They exist in a state of equilibrium. The inward pull of their own gravity is perfectly balanced by the outward push of their internal gas pressure. Think of it like a balloon. The air pressure inside the balloon pushes out, while the elastic skin of the balloon pulls in, holding its shape. In a molecular cloud, the internal movement of the molecules creates the pressure that supports it against its own weight. Look at a simulation of how gas behaves in a molecular cloud at minus 260 degrees Celsius, even at this temperature, with very little thermal energy. The random motion of the molecules is enough to keep the cloud puffed up, resisting collapse. The shape of the cloud is supported by this delicate balance. So, in order for these stable, lazy clouds to become stars, something has to happen. There has to be a trigger, a cosmic alarm clock, a shock. Something has to come along and violently upset this equilibrium, overwhelming the internal pressure and allowing gravity to finally, decisively win. And there are a few different types of these triggers, each more dramatic than the last. going back to our image of the pillars of creation. You can see one of these triggers in action in this very photo. Look closely at the outside of the pillars. You can see a sort of aurora, a glowing rim of light around them. This isn't just reflected light. This is the sign of destruction and creation happening simultaneously. What's happening is that the intense UV light from those hot, bright young stars outside the frame is blasting the outermost molecules of the pillars. It's a stellar hurricane. This radiation has a weathering effect, like ocean waves crashing against a cliff face. The excited molecules on the surface either get blasted away, escaping the cloud to join the surrounding H2 region, or they are pushed inward, ramming into the colder, denser molecules deeper inside the pillar. This creates a shock frontal wave of pressure that compresses the gas within. It's like squeezing a stress ball. You're applying external pressure, forcing the material inside to clump together. This pressure can also be created by an event of even greater violence, a supernova shockwave. A supernova is the death of a massive star, a topic we will get to in a later chapter. It is the most titanic explosion known to nature. When a star goes supernova, it unleashes a blast wave that races through the interstellar medium at thousands of kilometers per second. When this wall of pure energy slams into a peaceful, stable molecular cloud, it catastrophically compresses it. It's the ultimate cosmic hammer blow. It's interesting to me, and profoundly beautiful, that the death of one star can trigger the birth of 1,000 others. It's a celestial cycle of life and death written across the galaxy. The triggers can be even grander. You may remember me talking about density waves in previous videos. It's thought that molecular clouds simply passing through the spiral arms of the Milky Way regions of naturally higher density can be compressed enough to trigger collapse. And on the very largest scales, when entire galaxies collide, the immense gravitational forces can cause what is known as starburst within the galaxies. Starburst is when a galaxy produces stars at an extremely fast, frantic rate, and it can be seen in these brilliant blue knots of extremely hot young stars. The antennae galaxies are a stunning example of this. All of these triggers the radiation from newborn stars, the shock waves from dying ones, the passage through spiral arms. The collision of galaxies have the same fundamental effect. They destroy the equilibrium of the cloud. The internal pressure starts to give in to the relentless, patient pull of gravity. And when that happens, the show begins. Within the now destabilized cloud, the molecules begin to bump and shove against each other more frequently. In this chaos, tiny, random fluctuations in density suddenly matter. A slightly denser knot of gas will have a slightly stronger gravitational pull than the gas around it. This allows it to attract more material, making it denser, which increases its gravity, which allows it to pull in even more material. It's a runaway process, a positive feedback loop of collapse, depending on the size of the original molecular cloud. There can be anywhere from a few hundred to many millions of these collapsing clumps forming within it. Each one is a potential star. As the density of molecules in a clump increases, the interactions between them also increase. Friction and the sheer force of infalling material cause the temperature at the heart of the clump to start to rise. The higher density causes stronger gravity. More molecules from the cloud get pulled in by this increasing gravity. The temperature rises further, and gravity continues to increase. The domino effect is now unstoppable. These clumps, these infant stars in the making, are now what we call protostars. They are stars in their embryonic phase. They are not yet true stars, as they are not powered by nuclear fusion. Instead, their energy comes from the sheer violence of their formation. The gravitational energy released as countless, trillions of tons of gas and dust come crashing down onto their cores. The protostars keep growing, getting bigger and hotter, as long as the molecular cloud surrounding them keeps feeding them material. It's a cosmic feeding frenzy. And to graduate, to become a true main sequence star, a protostar needs to reach a critical mass. It needs to be at least 0.08 solar masses, about 80 times the mass of the planet Jupiter. Should the molecular cloud be dispersed too quickly by those same triggering forces, perhaps by the very stellar winds of its newly forming siblings, the protostar will be cut off from its food supply. If it hasn't reached that critical mass, its fate is sealed. It will become a failed star, a brown dwarf, a cosmic could have been. But what happens if there is enough mass? If the protostar successfully feasts and grows beyond that critical threshold, the process becomes even more spectacular. As material gets sucked in, conservation of angular momentum causes the entire system to begin to rotate faster and faster, like a figure skater pulling in their arms. The infalling material can no longer fall directly in. It flattens into a spinning, pancake-like structure around the protostar, called a protoplanetary disk. It is within this disk that the clumps that will become planets begin to form. And sometimes, bigger clumps in the disk can form their own disks. In fact, this is the most common outcome. Our Sun, a solitary star, is quite unusual in that respect. Most stars are born in pairs or multiple systems, all gravitationally bound, dancing around each other for billions of years. We should pause for a moment to let the scale of this entire process sink in. A typical interstellar cloud that begins this process is about 100 trillion kilometers across. That is roughly 10,000 times larger than the entire size of our solar system. Out to the Oort cloud, a single fragment of that cloud, which will form one or a few, is about 1 trillion kilometers across, still 100 times larger than our solar system. By the time the core of that fragment has collapsed into a true protostar, it will have shrunk to a size of about 10 billion kilometers larger than Neptune's orbit, and will have a temperature on the order of 10,000 degrees. As material is fed into these protostars, they can unleash their own powerful jets and shock waves back into the molecular cloud. This, in turn, can trigger further gravitational collapse nearby, leading to the birth of more protostars. It's a chain reaction of star birth. Eventually, after a few 100,000 to a few million years, a blink of an eye, in cosmic terms, the molecular cloud's material will be exhausted, blown away by the stellar winds of the brightest new stars. What is left behind depends entirely on the size of the original cloud. It could be a single star, a binary pair, a small cluster of a few hundred stars, a massive globular cluster of thousands, or even a whole supercluster of millions of stars. Some of these clusters will stay gravitationally bound for billions of years, while others, like our Sun, will eventually disperse, their member stars joining the general rotation of the galaxy. solitary travelers on long cosmic voyages. Imagine the most efficient power plant ever built, running perfectly for billions of years. Now, imagine what happens when its primary fuel source is suddenly cut off. The lights don't just flicker and go out. Emergency systems kick in. Backup generators, designed for short-term use, roar to life, straining under a load they were never meant to bear. The plant might even begin to consume its own structure in a frantic attempt to keep the power flowing. This is the precise, terrifying analogy for a star leaving the main sequence. The core, the primary reactor, is shutting down. The star, in its fight for survival, will unleash secondary systems of breathtaking power and violence. It will change its very structure, swelling to monstrous proportions, and in the process, it will fundamentally alter the architecture of any planetary system that orbits it. The death of a star begins not with a bang, but with a desperate, last-ditch effort to avoid that bang. And the first sign of this crisis is the buildup of a poison at its very heart. Helium ash. Let us zoom in on the core of a star like our Sun, a place where hydrogen fusion has been proceeding steadily for nearly 10 billion years. This process, the proton-proton chain, has been a model of efficiency, fusing 4 hydrogen nuclei protons into one helium-4 nucleus. But with each helium nucleus created, a tiny piece of the star's vitality is locked away. Helium, at the temperatures and pressures of a main sequence core, is inert. It is nuclear ash. It cannot fuse further at this stage. For billions of years, this hasn't been a problem. The core has been convective or radiative, constantly mixing or transporting energy, and the helium has been evenly distributed. But as the hydrogen depletes, the core begins to change. It becomes a stratified, layered structure. At the very center, a ball of pure helium ash begins to accumulate, a dead zone where fusion has ceased entirely. This inner core is still searingly hot, but it is no longer generating energy. It is a corpse at the heart of the living star. Surrounding this inert helium core is a thin, shell-like region where hydrogen is still abundant and fusion can continue. This is the hydrogen-burning shell. This shift from core fusion to shell fusion is a catastrophe for the star's stability. The elegant balance of the main sequence is shattered. Here's why. When fusion was confined to the core, the energy was generated throughout a large volume, providing a broad, stable base of pressure support. Now, energy is being generated in a thin, furious shell around a dead core. This shell is like a blowtorch aimed at the overlying layers of the star. The consequences are immediate and dramatic. 1. The helium core contracts, with no energy being generated within it to provide outward pressure. The inert helium core is no longer in equilibrium. Gravity, patient and relentless, immediately takes over. The core begins to contract. This contraction is not the gentle, slow process of the main sequence. It is a rapid, gravitational collapse. As it collapses, gravitational potential energy is converted into thermal energy. The core gets hotter, not just a little hotter, dramatically hotter. 2. The hydrogen shell burns fiercer. The heat from the collapsing core pours into the hydrogen-burning shell that surrounds it. Remember the extreme temperature sensitivity of fusion. The rate is proportional to T or more. A small rise in temperature leads to a huge rise in energy production. The hydrogen shell ignites with a ferocious intensity, burning far more violently than the core ever did. This is the star's backup generator, and it is being wildly overdone. 3. The outer layers expand. The massive surge of energy from the now superheated hydrogen shell does something counterintuitive. It doesn't push the core outward. The core is too dense and is still collapsing. Instead, this colossal wave of pressure pushes outward on the star's enormous envelope of gas. This envelope is violently heated and pushed outward. The star begins to inflate, and so the star embarks on a path of radical transformation. It leaves the main sequence on the Hertzspringer-Sohl diagram, moving swiftly to the upper right corner. It is becoming a red giant. Let's pause and consider the scale of this transformation. Our Sun, currently about 864,000 miles in diameter, will swell until its outer atmosphere reaches the orbit of Earth, and perhaps even Mars. Its diameter will increase by a factor of over 100. Its surface area will increase by a factor of 10,000, but as it expands, its surface cools. The same total energy, in fact, even more energy, due to the fierce shell burning, is now being radiated from a vastly larger, cooler surface. The surface temperature drops from a white-hot 5,800 K to a ruddy 3,500 K or less. The star glows with a deep, ominous red dot. This has apocalyptic consequences for any inner planets. Mercury and Venus will be unequivocally engulfed and vaporized. The Earth. The science is nuanced. As the Sun expands, it will lose a significant amount of mass through powerful stellar winds. This mass loss will weaken its gravitational grip, causing the planets to spiral outward into wider orbits. It will be a race against time. Will the Earth move away fast enough to avoid being engulfed by the expanding solar photosphere? Current models suggest it will be agonizingly close. Even if our planet isn't swallowed, it will be baked to a cinder. The oceans will boil, the atmosphere will be stripped away, and the surface will become a global sea of magma. The red giant phase is the ultimate sterilizer of inner solar systems. But the drama is not just happening in the envelope. Let's return to the core, where the real crisis is brewing. The helium core is still collapsing. It is being squeezed by the entire weight of the star. It has become degenerate. Degenerate matter is a state of matter that operates under quantum mechanical rules, utterly different from the ideal gas laws that governed the main sequence star. In a normal gas, pressure is determined by temperature. When you heat it, the particles move faster and the pressure increases. In a degenerate gas, however, the pressure comes from a quantum effect, the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state. As the core is compressed, the electrons are forced into closer and closer proximity, but they resist this forced intimacy with immense pressure. This electron degeneracy pressure is what supports the core against further collapse. Crucially, degenerate pressure does not depend on temperature. It depends only on density. This has a terrifying implication. The core is now supported by a quantum mechanical force that is oblivious to the thermal conditions inside it, and the thermal conditions are becoming extreme. The gravitational collapse is heating the degenerate helium core to phenomenal temperatures. It soars past 100 million Kelvin. At these temperatures, a new nuclear pathway becomes possible. The helium nuclei, which were inert at 10 million K, can now begin to fuse. The process is known as the triple alpha process because it fuses 3 helium for nuclei, which are also known as alpha particles. The process is fraught with difficulty. First, 2 helium nuclei must collide to form a highly unstable beryllium-8 nucleus, which normally falls apart in a mere 10 seconds. But within the dense, searing core, there is a small probability that a third helium nucleus will slam into the beryllium-8 before it can decay. This fusion forms a carbon-12 nucleus dot in a normal gas. The onset of helium fusion would be a gentle, self-regulating process. As the temperature rises, fusion begins, releasing energy that increases the pressure, which causes the core to expand and cool, thus moderating the fusion rate. It's a thermostat, but our core is not a normal gas. It is degenerate. Its pressure is independent of temperature. So, when the temperature finally hits the ignition point for helium fusion, the thermostat is broken. The fusion begins, and the release of energy causes the temperature to skyrocket. But because the pressure doesn't increase with temperature, the core cannot expand to cool itself. The rising temperature only makes the fusion reactions proceed faster, which releases more energy, which increases the temperature further. This creates a runaway thermal explosion, a helium flash. For a star like the Sun, the helium flash is one of the most violent events imaginable. In a matter of seconds, the degenerate core unleashes as much energy as the entire rest of the galaxy put together. It is a nuclear bomb detonating at the star's center. And yet, from the outside, you would see nothing, not a flicker. Why? Because the core is still degenerate and incredibly dense. All that phenomenal energy is absorbed by the non-degenerate layers of the core, lifting them out of degeneracy. The energy is used to transform the core back into a normal, ideal gas. The flash is entirely contained. It is a silent, invisible, cosmic heart attack. Once the degeneracy is lifted, the core can now behave like a normal gas again. It expands and settles into a new, stable equilibrium. Helium is now fusing steadily into carbon and some oxygen in the core. The star has found a new lease on life, a second period of stability. It shrinks somewhat from its maximum red giant size and moves to a different part of the HR diagram, known as the horizontal branch. For a time, it burns helium quietly. Let's follow the life of a brown dwarf from its failed inception. Once accretion stops, it is no longer being heated by infalling material. It begins to cool. It still has a tremendous amount of heat left over from its gravitational formation, and for a brief, fleeting moment, it might even achieve a peripheral, incomplete form of fusion. The first and only type of fusion a higher mass brown dwarf might briefly experience is deuterium burning. Deuterium is a heavy isotope of hydrogen with 1 proton and 1 neutron in its nucleus. Because the deuterium nucleus has a positive charge spread over a slightly larger area, it is easier to overcome the electrostatic repulsion. Deuterium fusion can ignite at a lower temperature and pressure than regular hydrogen fusion. Around 1 million degrees Kelvin, a brown dwarf with a mass above about 0.013 solar masses, 13 Jupiter masses, will burn its primordial deuterium supply. But this is a flash in the pan. Deuterium is exceedingly rare in the universe compared to regular hydrogen. The brown dwarf will burn through its entire supply in a mere 10 to 100 million years. After that, the fusion stops forever. For the very largest brown dwarfs, those skirting the 0.8 solar mass limit, there might even be a brief, sputtering period of lithium fusion. But again, lithium is even rarer. Its fusion is a last, dying gasp. Once this minor fusion ceases, the brown dwarf's fate is one of inexorable cooling. It has no internal energy source. It is like an ember pulled from a fire. It glows, but it is only a matter of time before it turns to ash. It radiates its internal heat away into the cold of space, following a predictable cooling curve. Over billions of years, it will slide down the spectral classification, starting as a relatively warm M-type, then LT, and finally to the theoretical white type, the coldest known celestial objects, with atmospheric temperatures cooler than a domestic oven. Because they are so cool and dim, brown dwarfs are incredibly difficult to find. They emit most of their radiation in the infrared part of the spectrum. There are certainly none visible to the naked eye in our sky. Their dim nature means our census of them is highly incomplete. For every star we see, there could be several brown dwarfs lurking unseen. The dark, silent majority of the galaxy's stellar mass objects. They are the ghosts in the machine, the unseen infrastructure of the cosmos, zooming in on Hubble's deep image of the Orion Nebula, however, reveals quite a few of these faint, reddish objects scattered amongst the bright, newborn stars. They are there, frozen in time, forever, on the threshold of a greatness they never achieved. What would it be like to stand on a planet orbiting a brown dwarf? It's a fascinating, if bleak, thought experiment. The brown dwarf would hang in the sky, a deep magenta, red, or dull orange orb, not bright enough to cast sharp shadows. It would emit little visible light, bathing any potential world in a perpetual dim twilight. The habitability zone, the region where liquid water could exist on a planet's surface, would be incredibly close in, and would shrink rapidly as the brown dwarf cooled. A planet would have to orbit perilously close, likely becoming tidally locked, with one side in permanent darkness and the other facing the dim glow of its failing sun. As the brown dwarf cooled, the habitability zone would march inexorably inward, forcing any fledgling life to constantly migrate or face extinction. The chance of complex life emerging and thriving under such transient and feeble conditions is considered slim. It is a haunting picture, a world huddled close to a dying ember in an ever colder universe. The existence of brown dwarfs teaches us a profound lesson about the universe. Nature abhors a vacuum, but it also enforces strict rules. There is a clear, quantitative line between a planet and a star, and it is drawn by the physics of fusion. The difference between a failed star and a brilliant sun like our own is a matter of massa, mere 0.08 solar masses. Had the clump that became Jupiter gathered just 70 times more material during the formation of our solar system, we would live in a binary star system with two suns in our sky. Our nights would be rare events. Our biology, our calendars, our very concept of day and night would be fundamentally different. It's a staggering thought, highlighting how delicate the conditions for our existence truly are. So, we are left with two paths. One leads to the brilliant, sustained fire of a main sequence star. The other leads to the slow, cold fade of a brown dwarf. For our story, let us now follow the successful candidate, the protostar, that gathered enough mass that withstood the chaos of the nursery, and that has just, at this very moment, ignited the fusion of hydrogen in its core. It has triumphed. It is now a star. But the universe is a place of endless variety. We have our newborn star, but what kind of star will it become? Why is our sun a steady yellow, while Betelgeuse is a bloated red supergiant and Rigel is a searing blue-white beacon? The mass it accrued during its protostar phase has not only granted it the gift of fusion, but has also irrevocably written its entire future, its color, its luminosity, its lifespan, and even the manner of its death. So, as our newborn star takes its first stable breaths, fusing hydrogen into helium, we must ask, how does this single attributite's birth mass dictate the entire spectacular and ultimately tragic destiny of a star? I want you to imagine a single number, a value imprinted on a star at its inception, a number that dictates nearly everything about its existence. This number is its mass. Think of it as a cosmic destiny written in the language of physics. A star with a little less mass will be a frugal, dim red dwarf shining for trillions of years. Long after the universe has grown cold and dark, a star with a little more mass will be a brilliant, profligate blue giant, blazing with the intensity of a million suns, but destined to burn out in a cosmic flash a mere few million years. Our own sun sits comfortably in the middle, a steady G-type star, providing a stable, nurturing light for billions of years. Why such a dramatic difference? The answer lies in the core, in the delicate and terrifying balance that defines a main sequence star. In this chapter, we will understand how this balance works, why it eventually must fail, and how a star's mass creates the incredible diversity we see in the night sky. We are about to learn the rules of stellar life, rules that are as beautiful as they are unforgiving. Let us freeze time for a moment, just as our newborn star achieves hydrostatic equilibrium. The inward crush of gravity, which has been the driving force of its collapse and formation, is now met by an equal and opposite outward push. But this push is not from gas pressure alone. That was the support of the protostar. This is different. This is the titanic force released by the conversion of matter into energy at the atomic level. The core of the star is now a cauldron of plasma at a temperature of over 10 million Kelvin and a density more than 10 times that of solid lead. Within this inferno, the proton-proton chain reaction is underway. Protons' hydrogen nuclei collide, fuse, and through a series of steps are transmuted into helium nuclei. With each fusion reaction, a tiny fraction of mass is annihilated, converted directly into energy as per E equals mc. This energy emerges as high-energy gamma-ray photons. These photons do not simply zip out of the star. The core is so dense that a photon is absorbed and re-emitted by atoms trillions of times in a random walk, a slow, meandering journey from the core to the surface. It can take a photon tens of thousands of years, sometimes even millions, to travel from the core to the photosphere. By the time this energy finally escapes into space as visible light, it has been downgraded from lethal gamma rays to the benign sunlight that warms our planet. This process, the slow diffusion of energy from the core outward creates a relentless radiative pressure that perfectly counteracts gravity's relentless pull. The star has found its balance. It is on the main sequence, but this balance is exquisitely sensitive to the star's mass. The mass of a star is its gravitational weight. More mass means a stronger gravitational pull, which means the core must be squeezed to higher densities and temperatures to produce enough outward pressure to resist collapse. This relationship is not linear. It is staggeringly exponential. The rate of nuclear fusion in the core is extraordinarily sensitive to temperature. A common estimate is that the fusion rate is proportional to the temperature raised to the fourth power T for the proton-proton chain, and an even more extreme dependence for other cycles. This means that if you double the core temperature of a star, the rate of energy production doesn't just double, it increases by a factor of 16. Let's put this in practical terms. Compare a very low-mass red dwarf, like Proxima Centauri, to a high-mass O-type star, like Zeta Ophiuchi. Proxima Centauri has about 12% of the Sun's mass. Its core temperature is lower, and the fusion reactions proceed at a slow, gentle pace. It is a miser with its fuel, using it so efficiently that it can shine for trillions of years. Its luminosity is a mere 0.0016% that of our Sun. It is a faint, cool, red ember. Zeta Ophiuchi, by contrast, is a runaway star with about 20 times the Sun's mass. Its immense weight crushes its core to a much higher temperature. The fusion rate isn't just 20 times faster. It's thousands, even millions of times faster. It burns its hydrogen fuel with a frantic, desperate intensity. Its luminosity is a staggering 90,000 times that of our Sun. But this profligacy comes at a cost. Despite having 20 times more fuel hydrogen, it burns it so much faster that its total lifespan on the main sequence is only about 8 million years, a cosmic blink of an eye. This relationship between mass, luminosity, and lifetime is the fundamental rule of the main sequence. It's why astronomers can plot stars on a graph called the Hertz-Prungressel HR diagram, and why the main sequence appears as a distinct diagonal band. Hot, massive, luminous blue stars are at the top left. Cool, low-mass, dim red stars are at the bottom right. Our Sun, a G-type star, sits in the middle. But if this were the whole story, the main sequence on the HR diagram would be a razor-thin line. Every star of a given mass would have the exact same temperature and luminosity. But it's not a line, it's a band. Why? Because stars age, and as they do, they undergo subtle but crucial changes. Even during this stable phase, remember, the star is fusing hydrogen into helium in its core. This means the composition of the core is slowly, inexorably changing. The ash of helium is accumulating. Helium nuclei with 2 protons have a stronger positive charge than hydrogen nuclei, making them more resistant to fusion at these temperatures. They are inert, dead weight in the core. As the core's hydrogen is gradually depleted and replaced by helium, the average mass of the particles in the core increases. To maintain the pressure needed to support the star's weight against gravity, the core must respond. It does so by contracting very slightly. This contraction has 2 effects. It increases the density, and more importantly, It converts gravitational potential energy into thermal energy, raising the core's temperature. This slow, gradual increase in core temperature has a direct consequence. It makes the remaining hydrogen fuse even faster. This causes the star's overall luminosity to slowly increase over time. Our Sun is a perfect example. When it first joined the main sequence 4.6 billion years ago, its luminosity was only about 70% of what it is today. Over the eons, as its core hydrogen has been depleted and its core has contracted and heated, it has grown steadily brighter. This has profound implications for planetary climates and the concept of the habitable zone, which slowly migrates outward over time. In another billion years or so, the Earth may receive too much solar energy for liquid water to exist on its surface, triggering a runaway greenhouse effect. The stability of our Sun is an illusion. It is a slowly turning dial, not a fixed switch. This gradual brightening is why the main sequence is a band on the HR diagram. A star like our Sun starts its main sequence life on the right-hand side of the band, cooler and dimmer, and slowly migrates to the left, hotter and brighter over billions of years. Now, let's add another layer of complexity: stellar composition. Not all stars are made of the same stuff. The interstellar medium from which a star forms is not pure hydrogen and helium. It contains traces of heavier elements, which astronomers call metals. A star's metallicity, the fraction of its mass made up of elements heavier than helium, has a significant effect on its appearance and evolution. A star with high metallicity, like our Sun, has more opaque plasma. The metals, with their complex electron structures, are very effective at absorbing radiation. This higher opacity acts like a blanket, trapping energy within the star. To transport this energy to the surface, the star must develop a steeper temperature gradient. This often leads to a larger, more puffed-up structure for a given mass. A high metallicity star will be slightly larger, cooler, and redder than a low metallicity star of the same mass. Conversely, a population-to star born in the early universe from metal-poor gas will be smaller, hotter, and bluer for its mass. Its plasma is more transparent, allowing energy to flow out more easily. These ancient metal-poor stars are like the pristine, first-generation aristocrats of the galaxy, their blue-white light telling a story of a time before the cosmos was enriched with the ashes of countless stellar deaths. So, we have three main factors that define a main sequence star. 1. Mass, the primary dictator of its temperature. Luminosity and lifespan. 2. Age, its position within the main sequence band, slowly brightening and heating as it consumes its core hydrogen. 3. Composition, which fine-tunes its size and color. This explains the wonderful diversity of the main sequence. But what about the stars that don't follow the rules? What about the ones that pulsate, that rhythmically brighten and dim? Look again at the HR diagram. You'll notice a region typically cutting across the main sequence and the giant branch, known as the instability strip. This is the home of the variable stars. A variable star is a star whose luminosity changes with time. The most famous examples are the Cepheid variables, which are massive, luminous stars that have left the main sequence, a topic for our next chapter. But there are also main sequence stars that pulsate like the RR Lyrae variables. Why here? Why only in this specific zone? The reason is a delicate and fascinating phenomenon known as the kappa mechanism. Kappa being the Greek letter for opacity. The physics is complex, but the principle is elegant. In the layers of a star located within the instability strip, the ionization state of helium creates a perfect engine for pulsation. Imagine a layer of helium that is partially ionized. When the star contracts, this layer is compressed and heats up. But instead of simply increasing the pressure, the heat goes into further ionizing the helium. Ionization absorbs energy without raising the pressure significantly. With the pressure support temporarily lagging, gravity wins, and the star contracts further. Once the helium is fully ionized, however, further compression does lead to a sharp rise in pressure. This increased pressure now overcompensates, causing the layer to expand. As it expands, it cools, and the helium ions start to recombine with electrons. This recombination releases energy, but again, without a corresponding drop in pressure. The pressure, support drops, and gravity takes over again, initiating a new collapse. The result is a continuous, rhythmic pulsation. The star breathes. It expands and contracts, growing brighter and dimmer in a perfectly predictable cycle. Some, like delta Scuti variables, pulsate with periods of just a few hours. Others have cycles of days or weeks. A breathtaking example of a pulsating variable observed by Hubble is Rs Puppis, a Cepheid variable. It's not on the main sequence, but its pulsation is driven by the same kappa mechanism. What makes Rs Puppis so spectacular is that it is surrounded by a vast nebula of its own ejected dust. Hubble imaged it over a 5-week period, and you can actually see the pulse of light traveling outward through the nebula, creating a spectacular light echo. Some rings are bright as the pulse from the star's bright phase passes through, and some are dark as the dim phase passes. It is one of the most direct and beautiful visualizations of the finite speed of light and the dynamic nature of stars. These variable stars are not just celestial curiosities. They are one of the most important tools in astronomy. In the early 20th century, Henrietta Leavitt discovered that 4 Cepheid variables, the period of their pulsation, is directly related to their intrinsic luminosity. A Cepheid that pulses with a longer period is inherently brighter than one with a shorter period. This period luminosity relationship became a standard candle, a cosmic yardstick that allowed Edwin Hubble to measure the distance to other galaxies and, in doing so, discover the expansion of the universe. The steady, rhythmic beating of these stars provided the first true measure of the cosmos. So, we have our main sequence stars, from the frugal red dwarfs to the brilliant blue giants, all fusing hydrogen in a stable, long-lasting equilibrium. Their properties exquisitely tuned by their mass, age, and composition. We have the pulsating variables, the rhythmic heartbeats of the instability strip, their regular brightening and dimming, providing a key to unlocking cosmic distances. It is a phase of magnificent stability and order, but it cannot last. The very process that provides the star's stability, hydrogen fusion, is also the process that sows the seeds of its destruction. With every second that passes, with every helium nucleus created, the core is changing. The fuel tank is being filled with ash. The balance of power is shifting, imperceptibly, but inevitably. The star is living on borrowed time. The main sequence is a golden age, but it is an age with an expiration date. The hydrogen in the core is finite. For a star like our Sun, this era will last a total of about 10 billion years. For a massive star, it may be over in just a few million. The clock is ticking. The helium ash is accumulating, and the core is slowly becoming a dormant, inert ball, cut off from the energy-producing regions. So, as our star continues its steady burn, we must look ahead to the coming crisis. What happens when the hydrogen fuel in the core is finally, utterly exhausted? How does a star respond when the very heart of its power plant begins to shut down? The end of the main sequence is the beginning of the end, and the star's final acts are its most dramatic. But this, too, is a temporary reprieve. The same tragic script begins again. In the core, helium is fusing into carbon and oxygen. Ash is accumulating. Eventually, the helium in the core is exhausted. An inert carbon-oxygen core forms and begins to collapse under gravity, becoming degenerate once more. Around it, a helium-burning shell ignites, and above that, the hydrogen-burning shell continues to rage. The star is now a complex, layered onion. At the center, a degenerate CO core. Then a helium-burning shell. Then a layer of unburned helium. Then a hydrogen-burning shell. And finally, the vast, distended, cool envelope with two powerful shell sources pumping energy into it. The star inflates once more, becoming even larger than before. It is now an asymptotic giant branch, a GB star, a true behemoth. Its envelope becomes so distended that its gravity can barely hold on to it. The star begins to pulse violently and in immense, convulsive gusts. It ejects its entire outer envelope into space. This ejected shell of gas, illuminated by the fierce ultraviolet light from the hot, exposed core, expands outwards, forming one of the most beautiful objects in astronomy, a planetary nebula. The Ring Nebula, the Cat's Eye Nebula, the Helix Nebula, these are all the glowing shrouds of dead stars, the final parting gift of a sun-like star to the galaxy, enriching the interstellar medium with the carbon, oxygen, and other elements forged in its core and shells. And what of the core? It is left behind as a tiny, incredibly hot and dense Earth-sized object, a white dwarf. It has no energy sources left. It is the exposed, degenerate, carbon-oxygen core itself, shining only by the residual heat of its past life. It will slowly, over billions of years, cool and fade to a black dwarf, a cold, dark crystal of carbon and oxygen. The final end for stars like our Sun. This is the fate we have been following, the path of low to intermediate mass stars. But what of the giants? What of the stars that were born with more than about 8 times the mass of the Sun? For them, the story is different. Their ends are not quiet. Their cores are not held back by electron degeneracy pressure. Their weight is so immense that they can continue the fusion process far beyond carbon and oxygen. In their final days, they become cosmic forges, layering element upon element in their interiors, a core of silicon and sulfur, surrounded by a shell of neon, then oxygen, then carbon, then helium, and finally hydrogen. They are living their lives millions of times faster than a star like the Sun, and when they finally build an iron core, they arrive at the end of the line. The formation of an iron core is the ultimate crisis. Iron is different. Fusing iron consumes energy. It does not release it. It is the ultimate nuclear ash. The star's final energy source is extinguished. The core, no longer supported by fusion, collapses in a fraction of a second. This is not a gentle contraction. It is a catastrophic implosion. And so, for the most massive stars, the desperate struggle to avoid death ends in the most dramatic way possible. What happens when a star's core, a sphere of iron more massive than our sun, suddenly has its support yanked away and collapses at nearly the speed of light? Imagine two siblings, born of the same cosmic nursery. One is cautious, frugal, and lives a long, steady life. The other is brash, extravagant, and lives fast and furiously. At the end of their lives, their passings could not be more different. One settles their affairs calmly, leaving a beautiful, orderly inheritance. The other goes out in a blaze of glory, their final act so powerful it reshapes the world around them. This is not a fable. It is the stark reality of stellar evolution. For stars like our sun, death is a poetic, almost gentle process. For stars, many times more massive, death is an apocalypse. In this chapter, we will stand as witnesses to both finales. We will watch the formation of a celestial Jula, white dwarf, and then turn to face the unimaginable fury of a supernova. And we will discover the profound truth that our very existence hinges entirely on which of these two paths a star takes. Chapter content. Let's first follow the path of the low to intermediate mass star. A star like our sun, with a final mass of less than about 8 solar masses. We left it as a pulsating, distended, asymptotic giant branch, a GB star. Its interior a layered onion of death, an inert carbon-oxygen core, surrounded by a helium-burning shell. Then a hydrogen-burning shell, all enveloped by a vast, tenuous atmosphere. The star is in its death throes. The twin shell sources are wildly unstable, causing the star to pulse with immense violence. With each pulse, its outer layers, held by only the faintest gravitational grip, are pushed further and further out. In a series of colossal, convulsive heaves, the star ejects its entire outer envelope, shroud of gas amounting to half its mass or more out into space. This ejected shell expands at a speed of tens of kilometers per second, a beautiful, glowing bubble of stellar material. But the drama is not over. The core of the star is now exposed. It is the hot, dense, Earth-sized carbon-oxygen core that has been building up over billions of years. This core, with a temperature now soaring over 100,000 Kelvin, unleashes a torrent of ultraviolet radiation. This UV floodlight slams into the slowly expanding shell of ejected gas, ionizing it and causing it to fluoresce with spectacular colors. Hydrogen glows red, oxygen glows green and blue. What we see is one of the most beautiful and misunderstood objects in the heavens, a planetary nebula. The name is a historical accident. Early astronomers thought their round shapes resembled planets. In reality, they are the fleeting, glowing tombs of sun-like stars. The Cat's Eye Nebula, the Ring Nebula, the Butterfly Nebula. Each is a unique and complex work of art, shaped by magnetic fields, binary companions, and jets. But their beauty is ephemeral. After only 10,000 to 20,000 years, the nebula disperses, its gas fading and mingling with the interstellar medium, enriching it with carbon, nitrogen, and oxygen, the fundamental elements of life as we know it. And what remains at the center? The exposed core, with no fusion left to support it. It is supported against its own gravity only by a quantum mechanical effect, electron degeneracy pressure. This is the same pressure that once triggered the helium flash. The electrons, packed shoulder to shoulder, simply cannot be compressed any further due to the Pauli exclusion principle. The core has become a white dwarf. A white dwarf is a fantastic object. It packs roughly the mass of the Sun into a volume the size of the Earth. A single teaspoon of white dwarf material would weigh several tons on Earth. It has no energy source. It is simply a blazing hot ember, the leftover heat from its former life as a star. It will shine with a fierce white light for billions of years, but it is cooling inexorably, destined to fade through yellow and red to a final, cold, black crystal of carbon and oxygen, a black dwarf. The universe is not old enough for any black dwarfs to exist yet. They are the ghosts of futures yet to come. This is the peaceful end. A quiet funeral, a beautiful shroud, and a diamond-like tombstone. It is a complete and closed cycle. But now we must turn to the other path, the path of the massive stars. For a star born with more than 8 times the mass of the Sun, its life is a frantic race against time, and its death is the ultimate cosmic spectacle. These stars live fast. They rush through their main sequence, lives in just millions of years. Then they don't just become red giants. They become red supergiants, like Betelgeuse, swelling to diameters that would engulf the orbit of Jupiter. Inside them, the fusion process does not stop at helium. Their immense cores, with temperatures and pressures far exceeding those in sun-like stars, act as layered nuclear furnaces. In the final days of a massive star, its interior resembles a cosmic onion. At the very center, the latest and greatest fusion product is accumulating. Surrounding it are concentric shells of previous ashes, an iron core, a shell of silicon and sulfur fusion, a shell of oxygen fusion, a shell of neon fusion, a shell of carbon fusion, a shell of helium fusion, a shell of hydrogen fusion. This star is building elements, layer by layer, all the way up the periodic table. Carbon, oxygen, neon, magnesium, silicon, sulfur, ... It is a stellar forge. But it arrives at a terrible impasse. Iron-56. Iron-56 has the most tightly bound nucleus of all elements. This means it is the end of the line for fusion. Up to iron, fusing elements releases energy, which provides the pressure to hold the star up. But to fuse iron into heavier elements requires an input of energy. It is no longer a power source. It is a power sink. So, the iron core grows. It is not degenerate. The temperatures are so high that the electrons are still a normal gas. But this support is temporary. The core grows until it reaches the Chandrasekhar limit, about 1.4 solar masses. At this point, even the immense thermal pressure can no longer hold it up. The core begins to collapse. What happens next is a sequence of events so rapid and violent, it is almost impossible to comprehend. The entire death spiral takes less than a second. Collapses at velocities reaching 70,000 kilometers per second, a quarter the speed of light. It shrinks from thousands of miles across to just a few dozen in a matter of milliseconds. 1. Photodisintegration. The energy of the collapse is so immense that it begins to break apart the iron nuclei themselves in a process called photodisintegration. Gamma-ray photons literally shatter iron into helium nuclei and free neutrons. This process consumes a colossal amount of energy, further accelerating the collapse to neutronization. The pressure becomes so extreme that electrons are forced to merge with protons in the core, forming neutrons and releasing neutrinos. The core becomes a soup of free neutrons. 3. The bounce. The collapse continues until the core reaches the density of an atomic nucleus. At this point, the neutrons, like the electrons in a white dwarf, become degenerate. Neutron degeneracy pressure suddenly kicks in and the core becomes rigid. The inner core abruptly stops collapsing. The still falling outer core, comprising thousands of Earth masses of iron, slams into this immovable neutron wall at half the speed of light. 4. The rebound. Shockwave. The collision creates a titanic rebounding shockwave that blasts back out through the infalling material. But this shockwave initially stalls, its energy being sapped by photodisintegration and the torrent of neutrinos pouring out from the newborn neutron core. 5. Neutrino rescue. For a tenth of a second, the fate of the explosion hangs in the balance. Then a miracle occurs. The intense flux of neutrinos, carrying away 99% of the star's gravitational binding energy, deposits a small fraction of their energy just behind the stalled shock. This neutrino heating is like pouring rocket fuel on a fire. It re-energizes the shockwave, which now erupts outward in a triumphant, unstoppable blast. This is a core collapse supernova. The shockwave, now traveling at hypersonic speeds, rips through the rest of the star, tearing it apart from the inside out. The energy released is almost beyond comprehension. For a few days, a single supernova can outshine its entire host galaxy of hundreds of billions of stars. The ejected stellar material, now a rapidly expanding cloud of incandescent gas, becomes a supernova remnant, like the Crab Nebula. This material is seeded with a treasure trove of newly synthesized elements. In the few seconds of the supernova explosion itself, the intense neutron flux creates elements heavier than iron like gold, silver, platinum, and uranium via the R-processed rapid neutron capture. Every piece of gold jewelry, every uranium fuel rod, every iodine in our bodies was forged in the heart of a dying massive star and scattered across the galaxy by its supernova explosion. And what of the core? It has been compressed into a neutron star, a city-sized object, typically only 20 kilometers across, yet containing 1.5 to 2 times the mass of the Sun, a sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. It is a perfect sphere of the densest material in the universe, often spinning at dizzying rates and possessing a magnetic field 1 trillion times stronger than Earth's. But there is a third, even more extreme possibility. If the collapsing core is so massive over about 2 to 3 solar masses that even neutron degeneracy pressure cannot halt its collapse, then no force in the universe can save it. The collapse continues forever. The space-time curvature becomes infinite. A black hole is born. We have now witnessed the two finales. One star leaves behind a diamond-like cinder, a white dwarf. The other leaves behind an ultra-dense, city-sized pulsar, or a bottomless pit in space-time, a black hole. These are the stellar corpses, the ghosts of stars past. But their story is not over. A white dwarf in a binary system can reignite in a thermonuclear holocaust. A neutron star can collide with another, spraying the universe with gold. These remnants are not inert. They can become the protagonists of new cosmic dramas. So, as we look at these bizarre endpoints of stellar evolution, we must ask, what happens to these stellar corpses? How can a dead white dwarf explode again? And what cosmic mysteries do the isolated neutron stars and black holes hold in their impossibly dense hearts? Look up at the night sky again. You see the bright, living stars. But for every point of light you see, there are countless invisible companions hiding in the darkness. Faint, Earth-sized embers containing the mass of a sun. City-sized spheres of pure nuclear matter spinning faster than a kitchen blender. And deepest of all, gravitational abysses from which nothing, not even light, can escape. These are the ghosts of dead stars, and they are not merely resting in peace. They can flare back to life in terrifying explosions, warp the fabric of space-time around them, and even hold the key to understanding the fate of the universe itself. Their silence is deceptive. In their incredible density and strangeness, they are shouting the secrets of fundamental physics. To understand them is to understand the ultimate limits of matter, energy, and reality itself. Let us begin with the most common stellar corpse, the white dwarf. This is the fate of about 97% of all stars in our galaxy, including our Sun. A white dwarf is the exposed core of a star, a ball of carbon and oxygen, or, for the lowest mass stars, just helium that has been squeezed into a volume no larger than the Earth. The physics that supports it is both simple and profound. Electron degeneracy, pressure. We met this concept during the helium flash. In a white dwarf, the gravitational crush is so immense that all the atoms are ionized, and the electrons are stripped from their nuclei, forming a sea of free electrons. These electrons are governed by the Pauli exclusion principle, which forbids them from occupying the same quantum state. They are packed together, shoulder to shoulder, and they resist further compression with unbelievable force. This pressure, which depends only on density and not on temperature, is what prevents the white dwarf from collapsing further. A white dwarf has no energy source. It is simply a blazing hot ember, radiating away the leftover heat from its billions of years of fusion. It starts its life with a surface temperature of over 100,000 Kelvin, shining a brilliant white-hot. Over billions of years, it will slowly cool, redden, and eventually fade to a cold, dark black dwarf, a crystalline sphere of carbon and oxygen, a diamond in the dark. The universe is not yet old enough for any black dwarfs to have formed. The first white dwarfs are still cooling, but a white dwarf's life can be anything but quiet, especially if it has a companion star. In a binary system, a white dwarf can gravitationally pull material, primarily hydrogen, from its stellar companion. This gas spirals down onto the white dwarf's surface, forming an accretion disk. Over time, the hydrogen layer on the surface builds up, becoming denser and hotter. Eventually, the base of this hydrogen layer reaches the critical temperature for fusion to ignite. But remember, the white dwarf itself is degenerate matter. The ignition of hydrogen fusion on its surface does not lead to a gentle burn. It triggers a runaway thermonuclear explosion, identical to the broken thermostat of the helium flash, but occurring on the star's surface. The entire hydrogen layer detonates in a matter of seconds. This is a nova, from the Latin for new. For a brief period, the system can increase in brightness by 50,000 to 100,000 times, appearing as a new star in the sky. The explosion blasts the accumulated material into space, but it does not destroy the white dwarf. The cycle can then begin again, with the white dwarf slowly siphoning more material and erupting in a nova every few 200,000 years. However, there is a more catastrophic outcome. If the white dwarf is close to the Chandrasekhar limit of 1.4 solar masses, and the accretion rate is high and steady, something far more violent can occur. The white dwarf can gain enough mass to push its core over the edge. The increased gravity overwhelms electron degeneracy pressure, and the carbon-oxygen core itself begins to fuse. The result is not a collapse, but a total thermonuclear incineration. In a fraction of a second, the fusion flame tears through the entire white dwarf, fusing carbon and oxygen into heavier elements like nickel and iron. The star is completely obliterated. There is no compact remnant. This is a type Ia supernova. These explosions are cosmic standard candles. Because they always occur at roughly the same mass threshold, they have a very consistent peak luminosity. This allows astronomers to use them to measure vast distances across the universe. It was by observing type Ia supernova in distant galaxies that astronomers made the shocking discovery that the expansion of the universe is accelerating, pointing to the existence of a mysterious force we call dark energy. So, the death of a white dwarf in a binary system helps us probe the ultimate fate of the entire cosmos. Now, let us turn to the remnants of core-collapse supernova neutron stars. If a white dwarf is strange, a neutron star is utterly alien, born from the collapse of a massive star's core. A neutron star packs between 1.1 and about 2.3 solar masses into a sphere only about 20 to 25 kilometers, 12 to 15 miles across. The density is mind-numbing. A single sugar cube of neutron star material would weigh over 1 billion tons on Earth, more than the entire human population. The support here comes from neutron degeneracy pressure, the neutron equivalent of what holds up a white dwarf. The collapse is so extreme that electrons are forced to merge with protons to form neutrons, hence the name. The entire star is essentially one giant atomic nucleus, a soup of neutrons, with a crust of iron nuclei and a potentially even stranger interior that may contain exotic states of matter, like superfluid neutrons or a core of free quarks. Neutron stars are born spinning incredibly fast, a result of the conservation of angular momentum from the collapsed core. They can rotate hundreds of times per second. Many also possess the most powerful magnetic fields in the universe, magnetars can have fields 1,000 trillion times stronger than Earth's. These intense magnetic fields, coupled with the rapid rotation, can turn the neutron star into a pulsar. A pulsar is not a pulsing star, but a lighthouse. The intense magnetic field channels radiation into two powerful beams emanating from the magnetic poles. If the rotation axis is misaligned with the magnetic axis, these beams sweep through space like the beam of a lighthouse. If one of these beams happens to cross Earth's path, we detect a regular, precise pulse of radiation radio waves, X-rays, or gamma rays, with a clock-like regularity that rivals atomic clocks. The pulsar, at the heart of the Crab Nebula, the remnant of the supernova observed in 1054 AD, pulses 30 times every second. Neutron stars are not always solitary. In binary systems, they can also accrete matter, becoming powerful X-ray sources. And sometimes, two neutron stars can orbit each other. As they spiral inward due to the emission of gravitational waves, they eventually collide. These kilonova explosions are the primary cosmic forges for the heaviest elements in the universe, like gold, platinum, and uranium. The gold in your wedding ring was likely born in the violent collision of two dead stars, billions of years ago. But what if the collapsing core is too massive for even neutron degeneracy pressure to hold? If the remnant core is above approximately 2.5 to 3 solar masses, no known force in the universe can halt the collapse. The matter is crushed into an infinitely small point, a singularity. The gravity around this point becomes so intense that within a certain boundary, called the event horizon, the escape velocity exceeds the speed of light. Nothing, not even light, can escape. A black hole is born. A black hole is not a cosmic vacuum cleaner. It is a region of space-time that is so warped that all paths lead inward. Our classical understanding of physics breaks down at the singularity. To truly understand it, we would need a theory of quantum gravity, which remains the holy grail of modern physics. Yet, we can study black holes through their influence. We can see stars orbiting an invisible, massive companion at the center of our galaxy, confirming the existence of a supermassive black hole named Sagittarius A*. We can observe the incredible light emitted by accretion disks of material spiraling into black holes, heated to millions of degrees. In 2019, the Event Horizon Telescope collaboration gave us the first ever direct image of a black hole's shadow, the dark silhouette of its event horizon, against the glowing accretion disk in the galaxy M87. This brings us to a final, profound reflection. Let's trace the journey of the atoms that make you, me, our planet, and everything we see around us. The hydrogen in the water molecules in your body is primordial, forged in the Big Bang itself. The helium is also mostly from the Big Bang, with a little from stellar fusion. The carbon and oxygen that form the bulk of your body's mass were forged in the cores of sun-like stars during their red giant phase, and then scattered into space by their planetary nebulae. The nitrogen in your DNA was likely produced in intermediate mass stars. The calcium in your bones and the iron in your blood that carries oxygen were forged in the interiors of massive stars. The iodine necessary for your metabolism was likely produced in supernova. The gold or silver in your jewelry was almost certainly forged in the collision of two neutron stars. Every heavy atom in your body was once inside a star. You are literally made of stardust. The carbon, nitrogen, and oxygen were blown out by the gentle death of stars like our sun. The iron, calcium, and iodine were blasted across space by the violent death of massive stars. The gold was minted in the collision of stellar corpses. We are not just observers of this cosmic cycle. We are a product of it. The universe forged the elements in stars, and then used those elements to build us. We are the universe's way of becoming conscious of itself. The death of stars is not just an end. It is a necessary step in the cycle of creation that led to planets, oceans, life, and to us. Sitting here, trying to understand it all, we have reached the end of our journey. From a cloud of gas to a conscious being contemplating its own origins. We have seen how stars live, die, and seed the cosmos with the elements of life. We have met their ghosts, the white dwarfs, neutron stars, and black holes that continue to shape the galaxy. The cycle is clear. From stardust we came, and to stardust we shall return. Our atoms destined to be recycled into new stars, new planets, and perhaps, one day, new life. So, I leave you with this final thought, a question not about the stars, but about us. If we are truly the universe's way of knowing itself, what will we do with that knowledge? What new stories will we tell when we finally venture out and walk among the ghosts of the stars that gave us life? Look at your hand. Seriously, take a moment and look at it. The skin, the bones, the blood flowing beneath the surface. It seems so mundane, so personal, so earthly. But I want you to see it for what it truly is, a collection of ancient artifacts. Every element in your hand, from the calcium in your bones to the iron in your blood, has a cosmic passport stamped with the explosions of dying suns. You are not just in the universe. The universe is in you. This connection is more than just poetic. It is the fundamental truth of our existence. In this chapter, we will explore the tangible consequences of this stellar legacy, how it shaped our planet, enabled our life, and now fuels our civilization. And we will look ahead to the ultimate human endeavor, our destiny to leave the cradle of Earth and become ourselves, a star-faring species. The universe began with only the lightest elements, hydrogen, helium, and a trace of lithium. For hundreds of millions of years, it was a pristine, simple place, incapable of forming rocky planets or the complex chemistry of life. The first stars, known as population 3 stars, were behemoths made purely of these light elements. They lived fast and died young in colossal supernovae, and in their deaths, they performed the universe's first act